So welcome to the 59th lecture of this surface engineering course. Actually, I'm coming back after quite some time. In between, we have covered almost everything that we wanted to. And before we wind up the course, I thought I would meet you once or twice more, primarily to impress upon you why did we study this course and what exactly would be the benefits, where are we going to use them, in what technological field, and what advantages or what benefits we can derive from this particular course content. If you look at this particular view graph, you realize we are trying to impress upon you as to why we need to worry about corrosion. So this is a major danger that actually threatens the integrity of metallic components, primarily metallic components, to a large extent. So if surface engineering is all about tailoring the near surface microstructure and composition and not affecting the bulk, then the obvious question is that why are we interested in modifying the surface alone and not catering so much to the bulk microstructure or properties? Well, actually, most of the material synthesis and development programs worry primarily about the entire bulk in various forms and dimensions, be it in the form of thin films all the way to bulk structures. But then we also have learned in the very first lecture that the threat always begins primarily at the surface, because the intensity of stress or mechanical activation is highest at the surface, and also the chemical attack always is most intense at the surface. So if we take, for example, corrosion as one of the possible dangers, then what we realize is that look at the figures. I mean, that's really staggering. Way back in almost 10 years ago, it used to be about 8,000 crore per annum cumulative loss only due to one single degradation process called corrosion. And obviously, corrosion means degradation of metallic systems in all forms of industry, be it manufacturing or petroleum, chemical, fertilizers, oil and petroleum, transportation, including automobiles, power sector, highway transportation, railways, aircrafts, almost everywhere. Wherever we use metals, the simple logic is the following, that Mother Nature preserves materials or metals in the form of more stable variation, which could be oxides or sulfides or hydroxides and so on and so forth in compound form. And if you are careless and we leave metal in the open and exposed to high temperature or even at room temperature to corrosive environment, then nature brings basically all these precious raw materials back to the pristine form so that it can be preserved for future. Which, in other words, nature always would like to see that nature doesn't look at it as degradation, nature looks at it as an act of preservation. So essentially what happens is that metal that we spend so much money, time and effort to win from its oxides always would like to go back to its oxide or any of the compound form whereby it cannot degrade any further or change any further. So for example, in US there's a estimate that it can cause something like over $270 billion per year. So this huge corrosion loss, for example, if you think of only steel and steel structures which are existing in the coastal areas where you have a lot of moist air, and the air also contains quite a bit of salinity and hence the presence of halide ions, particularly chlorine. So there it can actually lead to a huge loss of about 1,000 crore per year. Now, by and large, the statistics show that typically anything between 2 to 5%, not necessarily 4 to 5%, but 2 to 5% of the GDP is the total cumulative loss due to corrosion alone. Now, India is we are proud to be almost a $3 trillion worth GDP, one of the largest in the world, maybe third or fourth in terms of PPP. And typically about 5% of $3 trillion means about $150 billion or rupees 10,000 crore. So that's a huge sum of money which is wasted. And it is not wasted without any effort to arrest it, despite the fact that there is so much of, for example, all the railway wagons, you'll find that they are painted with a red oxide painting, which is an iron oxide painting. Similarly, all automobile bodies, all other buildings and metallic systems are never exposed as pure metal. They are always coated with some paint or coating or something. Yet corrosion occurs. Corrosion occurs because it actually is inevitable because of various complex synergistic action of mechanical, chemical, thermal and various kinds of other activated processes. But surface degradation is not only about corrosion. It can happen due to mechanical activation of wear or abrasion or erosion or corrosion at high temperature, oxidation, or actually more prevalent is the complex combination of, say, corrosion and erosion or corrosion and wear or oxidation in the presence of high fluidity or flow and so on. So you have interplay of mechanical as well as corrosive environment and various other activations. And this is exactly the reason why we need surface engineering. So that means surface engineering is an act by which we try to prevent this kind of degradations. So talking about corrosion, just a few examples. Here we are talking about galvanic corrosion or uniform corrosion. So if you have a steel plate, so this is a steel plate which is riveted, bolted on iron. This is a brass plate riveted on an iron background, and these are iron nails. So these iron nails, the rivets, which actually fixes the brass plate on top of iron structure and exposed to very corrosive environment in the coastal area, provides you a very nice couple, galvanic couple, where copper or brass will be more electropositive and iron will merrily corrode or becomes an anode and will actually undergo very easy dissolution. So you keep losing iron and iron forms rust, and this is a complex form of hydroxide, and because of the differences in its structure and specific volume, that means per unit mass, the crystal structure is such that the rust or iron oxide or iron hydroxide will actually expand when it forms, and hence creates enormous stress at the interface between the metal and the hydroxide, and gradually the rust, we all know, will spall off. And when the rust spalls off, then fresh iron is exposed and that gets oxidized and the process continues. So we keep losing a lot of iron from the surface as rust. So this can happen over the surface uniformly. We call it galvanic corrosion. If it occurs in a form which actually has a larger aspect ratio, meaning the penetration is deeper than the spread in the width. So as a result, you actually form these pits, small pockets, where the damage on the surface is not so wide, but the damage below the surface is much deeper, which is even more dangerous. So we can see either uniform corrosion or localized or pitting corrosion. Corrosion can happen in the underground pipelines through which water or sewer or any other form of fluid can actually be transported. Corrosion can happen to the hull of the seafaring voyager or a big ship, and once the ship comes back to from a long voyage, immediately it's taken into the dock and possibly also to the dry dock, and this whole body is now painted again. So first we have to scrape off all the oxides, all the rust, and expose fresh metallic surface. Then we use a primer and then one or two different coats of painting, so that in the next voyage it doesn't undergo the same amount of, we try to prevent corrosion. This can happen also not necessarily all in room temperature, but it can happen at high temperature. For example, the boiler tubes, we see an interplay of high temperature and corrosion or corrosion at high temperature and pressure. We also have to realize that when the flow is happening, for example, the ship hull, due to the waves, it certainly experiences some fluctuation of loading, but more or less over a period of time that's evened out. So we expect that, be it a big a pillar standing at the deck of near the sea coast, or any other static member, essentially experiences about the same level of stress. But then if you think of this kind of a bent tube, then obviously the amount of stress experienced at the top bend will be lower compared to the amount of stress which is experienced along the bottom rim. So obviously you expect a lot more damage occurring here. The effect of stress along with the high pressure of the steam and its oxidative action will be higher here. So we tend to see a lot of damages happening here. So this is what we were discussing, that in the ship hull, this is the joint essentially. So these are basically plates which are riveted, which are joined mechanically. So we certainly expect that corrosion can occur around these rivets, which may be compositionally different. And there's no necessity all the time we have to have pure copper and iron. We may have copper based or iron based alloys which are in the electrochemical series may actually form a galvanic couple by being one as electropositive, the other one electronegative, or cathodic and anodic. So corrosion can occur even in, and particularly maybe severe along these joints, and that's very dangerous, because if these corrosion at these joints actually penetrate, then obviously there'll be puncturing of the sheet, and obviously the ship cannot remain floated on in the water anymore. So we can also see such kind of damages are actually slow. For example, only few micrometers per year, but that's good enough to penetrate a sheet. You don't expect a sheet to be a few centimeter thick. It will be hardly a few millimeter thick. So if it is 10 micrometer or 20 micrometer per year, then obviously in 10 or 20 years the whole thing will puncture through and through. But in addition, this is in a static condition. So if you have stresses acting on it, then this puncturing can happen much earlier. We can also see a failure in the shaft, where, for example, here this portion is known to have undergone so-called bleeding, which essentially happens because of the fretting action, reciprocating action. So this is a shaft which is rotating, and during rotation the coating on the surface is peeled off, and this is where it actually undergoes. So the fresh iron bearing portion gets exposed and corrosion happens here, and then a lot more metal value actually comes to the fore, and these metals form rust, and then they spall off, and then fresh metal comes out in contact with the corrosive atmosphere, then undergoes corrosion, again spalls off. So this continued rusting essentially is almost like bleeding gradually from inside, as if blood is oozing out or metal is oozing out. In all these cases, I'm just giving you examples which are all from practical cases. Say, for example, a huge bridge over a river or over a railway track or over certain distances, and you have multiple members, and it cannot be a monolith. Obviously you have joints, and these joints could be welded joints, could be riveted joints, and in fact you may have joints between two members which are compositionally not exactly the same. And I told you already that there is always a danger if you have compositionally different members joined across a particular point, because now these two members, because of their compositional difference, can have different electrochemical potential, and as a result one can act cathodic in comparison to the other, which may be anodic, and the anode portion will start leaching or dissolving faster. So we need to prevent rusting on the bridges, and that's why you'd find all the bridges are painted, and painted not just once, painted periodically. And in fact, structural health monitoring of these bridges is a very, very important activity for railways, for the Public Works Department, or all other custodians of these structures. So this can also happen, corrosion can also happen in an oil tank. And now you imagine, we always thought that the atmosphere is the culprit, but this could also happen, such severe damage can also happen because of the bacteria or microbes who actually tend to feed on metal. So if you have a portion of a metal which apparently is not revealing much of a damage because it's immersed under water or some other fluid, and in a static condition it may allow actually bacteria or microbes to grow around the surface. And if the coating or if the protection is peeled off, and if the fresh metal is exposed, then these bacteria can actually come and gradually grow. It can be not just bacteria, it can be borne through algae or fungi or various other microbes or microorganisms which actually for some reason manage to peg to some corners or crevice. And if that happens, then basically they gradually multiply, they grow, and when they grow they start feeding on the metal. So they penetrate and they can create such a huge hole, and once such hole forms, then obviously this oil storage tank is no good anymore. So one has to, now there is no escape from it, because you actually have to have petroleum, and in order to store you need metallic vessels, and the petroleum will contain a lot of sulfide or sulfur containing fluid, and there are bacteria which are called sulfate reducing bacteria who actually will feed on such stock, and then in the process will actually cause such corrosion, even form such holes. Materials can degrade over a period of time because of various other possibilities. So even before corrosion starts, because of the environment or interaction with the environment, there could be gradual loss of alloying elements. So for example, when we talk of brass, we know that in brass we are talking about copper alloyed with zinc, and this zinc is the element which actually provides the strength and various other important properties. Now if you expose this in a chloride containing atmosphere, so gradually the zinc can be leached out gradually by the action of these chloride containing maybe HCl, or simply the chlorine in water can actually preferentially attack zinc and then dissolve zinc. So you may actually gradually create a region, a localized region on the surface, which because of some mechanical or some other reason probably has developed a perforation, and that perforation can actually allow the chlorine ions to gradually seep through and attack, dissolve zinc, and then in the process you lose a lot of zinc. So instead of, let's say, 30% zinc, after a period of time this may reduce to as low as maybe 5 or 10%. So obviously it's not only the mechanical strength which reduces in this region, even the electrochemical behavior, the potential of this region also is drastically changed, and that leads to a lot of failure. So we also would have seen all these brass wires, brass wares, the brass plates, flower vase on various kinds of art objects and so on. And this kind of bluish grain corrosion products, patina, is very common to form on such brassware or brass plates, even copper plates and so on. So these are again corrosion products, some kind of a sulfide, and these are because of the continual corrosion happening. So not just oil tanks or oil pipes or huge ship hulls or rivets and nails or simply iron structures, pillars or bridges, steel structures, in not even all these art objects, even in miniature electronic devices, you do have the possibilities of corrosion. In fact, in most of the cases, the logic, the architecture of the device doesn't fail, the materials may fail. And when the material fails, then it leads to some kind of a short circuit or certain other kinds of problems. So if you look at these regions, just zero onto these regions, you do realize that the color is different here. And Actually, we are all aware that in microelectronic devices, locally at a particular junction, the voltage can be fairly large, and the current flow in limited region could also be fairly high. So it can cause local heating, and in fact heat dissipation. For heat dissipation, we do allow airflow as a means of heat extraction. We also must realize that the whole electronic circuit is embedded in a package or a polymeric substrate in which all these electronic components are embedded. Now, for connection, for completing the circuit from one particular device to another and make the whole chip as an integrated chip, we do use joining by way of either soldering or some cases even brazing. That means we are using a filler metal, and the filler metal actually causes localized fusion or melting of the metallic parts between two different sides, and compositionally they are very close but not exactly the same. So typically you can use lead tin solder. These days lead tin solder is not used anymore. So you may have, let's say, indium tin or say indium gallium tin or some other forms of low melting eutectic compound. Now compositionally they are very different than the aluminum or gold or whatever form of metallic interconnects you have used. And obviously they alloy well, because when you heat and melt during soldering, obviously you form a local globule, molten globule, which has unlimited solubility. So it will immediately dissolve some of the metals around, and as a result the composition of the wires and interconnects will change. And more importantly, it also allows easy electron flow even when the circuit is not on. So in other words, because of the presence of moisture or any other form of corrosive attack, it can actually undergo very slow but definite dissolution, and as a result of which there could be corrosion damage, and then eventually these systems can fail. So it's not just the big large equipments, even miniature tiny little microelectronic devices, even your watch or a cell phone or a computer, laptop, all of them are prone to such degradations. So such degradations or possibilities of degradation is ubiquitous everywhere. You can't prevent it altogether. So it's not, I told you that it's not alone, there's no necessity that only chlorine ions will come in contact with something and then cause corrosion, or simply hydroxyl ion will cause the first damage and so on. This could always be because of various combinations of attacks. So for example, we are aware that in the pre-stressed concrete structures, which because the pre-stressing of the reinforcing steel wires or bars, the concrete structure as a whole develops. So if this is the structure we are talking about, and if we have such reinforcement of steel cords or rods or wires, and if we pre-stress them, that means if we, for example, at these two ends, if we start applying certain torsional effect because of application of screw or some other activity, so that means basically this length will undergo some kind of a stress, will develop some kind of a stress. And when you cast, then this stress will actually create a residual state of stress on the surface of the concrete, which will be compressive in nature, acting towards each other. So the material, when you actually release, will tend to relax, will tend to actually expand, because you applied some mechanical forces to compress them. So when they try to relax, then they try to actually stretch along with the concrete, but by then the concrete is all cast and frozen, so it cannot allow the rods to stretch anymore. So in the process it develops a residual stress on the surface, which acts in opposite direction or compressive in nature. Now even in order to get this effect of residual compressive stress, use of such reinforcements which actually produce residual compressive stress is very important. But the steel and concrete interface is always a very probable spot for corrosion or damage to occur, because you are crossing over, there will be some amount of gap, and that gap obviously for the structures you can't see that from the open from outside, but the length scale of such air gap could be of the order of a few micrometer or even less. Nevertheless, this also is the region where you expect some moisture to be trapped, because for setting the concrete you do all the time water, you all the time add water. So these kind of concrete structures will always have steel or metal concrete interface, and there could be certain amount of corrosion happening because of the trapped moisture. And in fact, they actually vastly depend on the presence of the chloride contamination or the pH level, the acidity or basicity level, and also they are influenced by stray DC current, direct current, presence of them. So in fact, these structures are actually given certain open circuit current, so that which is in the opposite direction, so that the corrosion current is mitigated and the effect of corrosion is reduced or remedied. So unless we take care of that, there could be sudden bursting failure of the pipes, and that could be very dangerous. So similar corrosion can occur in case of water pipe going underground or even overground. We may see, I already mentioned that the combined effect of pressure, temperature at an elevated temperature condition can cause much more damage to a steel tube, for example, a pressure vessel. So you, for power generation, you need very high amount of, very high pressure of vapor. So you actually boil water in the boiler, and then you allow the steam to escape, and that steam escapes through a tube called the pressure vessel tubes, and those tubes are exposed to such high temperature and pressure condition before they actually interact with the turbine. So these ruptures are very common in the pressure vessel tubes, and when such rupture happens, then either you chop off from these two ends and then bring in another piece of tube and then join by welding at these two spots. Then these welding joints become again another possibility of future failure region. So one has to be careful about them. So there could be also failures in pipelines, which is basically joint. And in the joint, in many cases, we don't quite realize, we tend to believe all are iron, but actually they may have certain, they may be brass with certain amount of coating on top of that. So we don't know really, but if there's a compositional difference, so for example, one can easily see that there is a compositional difference because of which maybe there was a copper and iron combination or interface because of which a lot of corrosion took place, and there could be failure like this. So failure also is very common in dry cells, the storage batteries. If you leave it unused for a long time, for example, inside your torch or in your radio, you would have seen that if you remove the battery after a few months, you would have forgotten, and then when you try to remove, they tend to stick inside, and when you take out, you see some fluid coming out, oozing out, which are the residual acid, and this is the result of such corrosion. Such perforation or leakage happens because of corrosion. So you actually have zinc, you do use zinc as an anode and carbon as a cathode. So obviously zinc will always, in fact the current is because of dissolution of zinc or oxidation of zinc. So for every set of electrons released from zinc, you do realize that some amount of zinc is being dissolved and going into solution. And that solution, so over a period of time, the zinc surface, which is a body and which is acting as the anode, may actually develop such perforations or corrosion leakages or spots through which acid may ooze out. So I mean, if you have a dry cell, there is no escape from having a combination which gives the highest possible current, and zinc and graphite rod would be an ideal combination. But if you do that, then over a period of time, when you have extracted as much potential as possible, then you are bound to see some amount of perforation or damages created onto the surface. So it's not that if you are careful enough, you can completely prevent corrosion. You cannot, because the whole action of battery power generation itself is corrosive in nature. So you have to be careful enough, so there has to be a life, and beyond that life you have to discard and replace with a fresh battery. Look at these impellers or these propellers of a so this is the shaft on which this propeller is rotating, and these blades, they actually also undergo a huge amount of erosion corrosion combination of them. So mechanical forces along with airborne moisture and other gases. On the other hand, apart from corrosion, or which actually requires an electrolyte, so typically for a corrosion to occur you need anode, cathode and an electrolyte. If it's high temperature, obviously a single electrode degradation can happen, which is typically the case of oxidation. But room temperature or high temperature mechanical activation can lead to a lot more damage, lot severe damage called through a process called wear. So and you know very well that two mating surfaces or surface and a flowing medium solid, all of these can actually cause damage to each other because of frictional forces or because of surface asperities interacting with each other. So they can be because of reciprocating nature of motion, they can be because of temporary cold welding between the two mating surfaces, or because of particles or surfaces having certain amount of roughnesses and interacting to smoothen out the roughnesses and forming such degradation of material. It can be also because of the rotating or alternating stress cycles, and such severe damage can happen onto the rim of a tire or of a wheel. Such erosive wear can happen in the piston of a pump, because of during rotation it probably can interact with fluid which carries some particles in them. This is the engine bore, the bore of an engine, automobile engine or some other IC engine, and the piston moves up and down, and you can easily see that you have longitudinal marks in the inner surface of the piston, and these marks essentially represent the wear damages caused by the piston moving up and down. In fact, one of the key design element here would be to make sure that you have enough lubrication between the piston and the inner bore wall, so that they don't foul with each other or they don't come direct contact with each other. A very thin lubrication film should actually make sure that they don't rub against each other non-uniformly. So the overall engine block, the function of the engine block to a large extent will depend upon the functioning or prevention of wear at these positions. So similar things can happen in all other rotating or members or components which are undergoing various cyclic deformation or cyclic motion, which could be in the bearing, it could be in the shafts of a lift or an elevator or a chain pulley system. On the gear systems like this, you are seeing all these roughnesses developed because of these are the teeth of the gear which is rotating, let's say like this, but during rotation it actually undergoes such wear at the teeth. One very important aspect is this turbine engine. In fact, I would have mentioned earlier also that this is the marvel of engineering, that in this compressor part or in the high temperature turbine zone, the combustion zone, the temperature here could be in excess of somewhere around 300, 400, 450 at the most. So 300 to 400 degrees centigrade. So you are happy using titanium alloy. And this titanium alloy certainly undergoes oxidation, but there's a limit. We know exactly what would be the life of these blades here, compressor blades. Here the temperature is much higher, something like about 1050 degrees centigrade. So obviously at this high temperature, the nickel-based superalloy turbine blades actually undergo, the biggest threat they actually have to, one has to take care of is the oxidation at the very beginning. Then comes all others like high temperature creep or high temperature strength requirements to prevent erosion and various other processes. So these are all surface damages. So Even in this side, when you are sucking in air, so along with air you may suck in a lot of solid particles. So the turbine blades undergo very severe hit from the sand particles or whatever particles get sucked in. So these titanium alloys should have sufficient erosion resistance, right? Here, apart from more than erosion, because by now you don't expect so much of particles to flow all the way there, but you certainly expect much higher temperature and high temperature attack. So you have to take care of the thermal fatigue, the creep damages, because you are subjecting to elevated temperature at constant load, and most importantly oxidation at that temperature. Now when you want to prevent oxidation of nickel based superalloy, you have to realize that if the body is made of some nickel based alloy, then on top of that ideally you would like to have coatings of, let's say, zirconia. Okay. Now zirconia, obviously if it can bond well with nickel, there is no problem, then it can prevent counter ionic transport. For nickel to undergo oxidation, you require the cations, the nickel, to go out and anion, the oxygen, to come in. So if you can create a barrier here in the form of this zirconia, then these nickel ions or iron ions, they actually are not able to go and meet the oxygen oxide ions coming from the air, and hence the oxidation can be prevented. But the biggest problem is that how do you make sure that this zirconia, which has a direct band gap and which is oxide having a very different crystal structure, very different coefficient of thermal expansion, density, and all those physical properties than the base metal based on nickel. So the bonding between these two becomes the biggest challenge. So all the aircraft manufacturers, for that matter, all high temperature metallic systems would always love to create a technology which actually can allow them to combine the oxide with the metal very nicely and very efficiently at the interface. To even going beyond the Earth's surface, if you want to be an astronaut and plan to go to the moon and come back, then you would require such a reusable vehicle, space shuttle. So for reusable space shuttle, if it has to go to the outer space and come back, the regions which actually will undergo the biggest temperature threat would be all these portions. So the leading edges, the fins, the nose cone, and so on. So the temperature here could be in excess of 1500 degrees centigrade. So now we are talking about a temperature regime which is even higher than the turbine blade temperatures. So obviously you require tiles, or you require ceramic systems which actually can prevent such high temperatures. So now we are talking about this high temperatures, and this is the temperature distribution. As you can see, that varying temperatures, and in addition to that there will be an enormous amount of pressure, force of air which these leading edges and the nose cone will have to withstand when it will try to return from very rarefied condition in the outer space and enter into the Earth's atmosphere, which is pressure wise much higher. So the frictional forces will raise the temperature immediately to such high values, and this can cause a huge threat to the structural integrity of the system. The infamous disaster for the US space shuttle, which was trying to enter, and we lost one of the finest scientists and astronauts, Kalpana Chawla, in that accident. That happened primarily because the heat resistant tiles from the nose cone actually fell off, and when they fell off they exposed the metal inside, and the metal came in contact with air at that high pressure at that point, and in no time the metal actually got heated up to such an extent that it caught fire. And once metal gets to temperatures in excess of several thousand degrees centigrade, even a single spark can immediately convert this whole structure into a fireball. So you can't prevent that. So in order to prevent any such accident from happening, you have to have a very good protection system here. So that's again is an activity which is only at the surface, not necessarily for the entire bulk. So you can't make a zirconia complete zirconia based shuttle that's too brittle, and mechanically there will be very little toughness available. So it has to be a metallic system, but with the protection of these kind of ceramic coating or tiles which can prevent such high temperatures. So these are all about, so far we have discussed all about these inorganic systems, mostly various either static or dynamic systems. But what about human body itself? I mean, that's also another region where threats of various forms actually pose a huge danger and a challenge. In fact, we are all aware that for various orthopedic reasons, maybe an accident, maybe deformity, maybe illness, maybe degradation over a period of time like this, the senior people, the aged people undergo hip joint replacement or knee joint replacements and so on like this. So in various forms, these structure is made up of ceramic materials. I mean, essentially the bone materials are all calcium, various forms of calcium based inorganic compounds, ceramic materials. And these are the regions, say the elbow, the knee, the hip, and even the fingers. In all the places we have various joints, even along this vertebra. So everywhere we have, so essentially these are ceramic systems which are subjected to various kinds of loading, various kinds of forces, and of very irregular type. They are not necessarily all the time. You don't carry every time the same load. You don't walk exactly on the same road, or you don't run on the same terrain, or the vehicle you're traveling in can cause various kinds of vibrations which are not exactly the same. So the body is subjected to various kinds of mechanical forces and thrusts, and as a result of which there could always be damages at these joints before any other place, or because of accident or a blow there may be a fracture in the bone or somewhere. So you need to replace them, and when you try to replace them, you have to realize that you can't replace them with metal. For example, if you replace one leg with a metallic system, then there will be a huge density difference and weight difference, so you possibly cannot walk. So you have to, ideally you would like to develop a material whose core will be metal like this, but will have a coating of some compound which could be very close to the bone composition, something like hydroxyapatite, which actually can also integrate well with the body. So body fluid may cause corrosion and damage and start leaching from this metallic stem, which could be, let's say, titanium or maybe stainless steel or cobalt based alloys or something. But then if it is coated with hydroxyapatite, then the body fluid actually doesn't cause any damage, and on top of that there could be natural bone growth on this or tissue growth on this, and the metallic system can integrate well with your body over a period of time. So this is also a surface engineering activity, highly a surface engineering activity. For an unfortunate cancer patient, if you have removed this part of the bone, and if you want to replace with a metal piece like this, the surgeon will be find it very easy to do that. In no time he'll do it, but this portion will undergo huge amount of corrosion over a period of time, and very soon you may have to replace it back again. So you need to protect this, and in order to, while you are trying to protect this metallic system, protect from leaching due to the interaction with body fluid, you actually have to take care of the surface, and that's surface engineering. You may need it for various kinds of mechanical activation or interaction. You may also need to create the tip of an electrode, which for example, neurons are nothing but electrodes through which the body exchanges information in the form of ionic transfer, and the typical dimension of the tip of such an electrode or neuron would be in the order of a micrometer. So if such neurons get damaged or for whatever reason stop functioning or starts malfunctioning, and if you want to replace with an artificial neuron or artificial electrode, so you have to have a tip which is as thin as a hair, a few tenths of a micrometer, And on the tip, you may also like to create such very intentionally, you want to create such highly irregular and rough surface, so that the specific surface area is a lot higher, and you can actually allow lot more ions to be exchanged with the fluid around, and that's how you can actually allow information to be exchanged very efficiently. So all these examples I thought I would bring to your notice. Is you studied so much about anything starting from surface engineering of steel to various non-ferrous metals, even bit of polymers and ceramics, and you studied diffusion based, thermally activated, various kinds of coatings, various kinds of mechanically activated systems, and so on. All these are essentially various approaches and various possibilities of trying to protect the surface, primarily metallic surfaces, from corrosion and various other kinds of damages. So these are the case studies for you to, if you ever encounter a question from within as to why did I study surface engineering, then today's lecture and all these slides are there to help you to answer as to why surface engineering is so important. Okay, thank you very much.